Good morning. Today we are going to be talking about the theory of evolution. I always like to take a moment or two right before we start talking about this new unit to express and share with you that as part of our state standards, we have to teach the theory of evolution. And with the theory of evolution, there comes a lot of ideas about how Earth and how we came to be. And I just want to address them that's okay. You're entitled to your opinions. You're entitled to your beliefs. What we're going to be focusing on in the lesson today and throughout the rest of the week is talking about the evidence to support the theory of evolution. As you know, when we talk about theories in science, there's a lot of evidence to kind of hold stand or withstand that theory. So when we go through today's lesson, the major ideas for to support the theory of evolutions are as follows: the fossil record, homologous body structures, vestigial organs, embryology, and then biochemical or DNA evidence. So with that being said, I just want to share with you that we all come from different backgrounds, we have different beliefs and different opinions, and that's okay. What my curriculum or our curriculum here in eighth grade, as well as our state standards, talk about is the evidence. So that's really what I'm going to focus my lesson on today. Not necessarily kind of where we came to be or how we originated or any of those ideas. I'm going to be centered. It's really going to be centered on the evidence. You think about in language arts class, you have to have evidence to support your claim. So I'm giving you the pieces of evidence. Some of you guys, by the end of this unit, say, I don't really agree with the evidence, and that's okay. But again, from a scientific perspective, the theory of evolution, these are the pieces of evidence. I also would like to share with you that when you talk about evolution, evolution, by definition, is going to be a change over time. And I always like to share this idea that change is always happening every second of every day. And that's the only thing that is actually constant is change. So with that being said, we're going to get started and we're going to talk about first the fossil record. So we've
got mail.
So we've talked about the fossil record before at length because we talked about it in our Earth Science unit. So fossils are a way for scientists to record the history of life on Earth. And it tells us a lot about our world when we didn't exist on it. So what does the fossil record tell us about the organisms? It can kind of give us an inference as to what does it look like, what's the shape of the organism, how or where they lived, what other organisms they coexisted with or lived with, what time period did they live based on the locations and rock layers. You should know that the newer rocks, if you look over here, are the newer fossils versus the older rocks or the older fossils. So over time, in the sedimentary rock, that's where you're going to find fossils. You can kind of see those sedimentary rock layers and the different fossils that are embedded in that in those different layers. So you can see, for example, over here that these two fossils coexisted, all right, just based on the locations in the rock layers. And then the order of living things that they came in. So the deeper rocks, they're older rocks, which means they're older fossils, and then up top would be the newer rocks. Okay, so that's called the law of superposition on the fossil record. You can also tie into the fossil record dealing with the concept of Pangea. We talked about Pangea when we talked about Earth Science unit, how kind of all the continents once were one, and then over time through plate tectonics, our countries kind of moved apart slowly over time. And then you could see just over time over here in this visual, the fossil record. So that's your first piece of evidence. Fossils are a really big piece of evidence to support the theory of evolution, just because that's what we know to be of our historical past. Next is something new, and I'm going to show you these little visuals here. I'm going to X out of this box so you can see a little bit better. Homologous body structures. If you look at the root of that word, homo means same. So body structures that are similar in structure but different in function. And they're due to the sharing of a common ancestor. And I'll give you an example of this. I'm a visual learner, so I think this will really help you. So you can see here, this is the humerus. Think of your arm, the humerus of a human. Then you have your radius and your ulna, which are kind of like your lower arm bones. Then you have your carpals and metacarpals and your phalanges. That's basically the bones of your hands, right? Okay, so let's think about a human. So if you look at a dolphin, for an example, that dolphin in the pectoral fins has those same bone structures. It has a humerus, a radius, an ulna, a carpals, a metacarpals, and phalanges. Again, they're similar in structure, but they have a different function, right? Because we use, as humans, we use our hands to grasp objects. Dolphins don't use their pectoral fins to grasp objects. They use them to swim and to move and to be directional, right? So same structure, different function. Same thing here with the bat wing. Okay, you can see those same bone structures: humerus, radius, ulna, carpals, metacarpals, and phalanges. So you see all those same bone structures, but as you know, a bat's wing is used for flying. Okay, so grasping objects, swimming, flying, and then same thing with the bird wing, okay, for flying. Okay, so these are all your examples of homologous body structures. They have the same structure, but a different function. This all kind of culminates into this a phrase that you'll hear a lot of us talking about, you'll be reading about, that we all share a common ancestor. Okay, and that kind of points to the theory or the evidence behind the theory of evolution. Again, this is just another visual. You can see a turtle, an alligator, a bird, and a mammal. We can kind of trace them back in evolutionary time, and we can say that we all probably, all these organisms here, whether mammals or not, reptiles, obviously, that they probably shared a common ancestor of a lobed finned fish, okay, because they have all that same bone structure, okay, so we shared a common ancestor. Here's another visual, okay, showing comparing a human, a cat, a bird, a human, cat, a whale, and a bat. Again, you see those same bone structures in all of those organisms, but all used for different functions, okay, so grasping, walking, swimming, and flying. Okay, so all something called homologous structures. Again, homo meaning the same, so same structure, different functions. The third piece of evidence to support the theory of evolution is something called vestigial organs. Vestigial organs, sorry, just wanted to make sure I was still recording. Vestigial organs are leftover traces of evolutions that serve, quote unquote, no purpose. So these are structures, organs, bones, things in us as humans or all other organisms, because all organs have all organisms have vestigial organs, of things that don't really have a purpose anymore. So you can see some examples like our tailbone in humans, okay, our appendix. No real use for it, but we still have it. Limbs in whales. If you look at the skeletal structure on some whales, they actually have like a pelvic bone, or structures that look like they were limbs. Okay, to walk on water. Okay, or not walk on water, walk on land. So if you think of that as a whale, okay, do whales need limbs? Not really, right? They have those fins. So they're vestigial organs. Here's another example. In snakes, you see a femur representing a hind limb. Snakes don't need them, right? They don't have legs, but humans do, right? So vertebral column, pelvic girdle, again, you'll see that in snakes. We need it as humans, okay? But the coccyx, you can see here in the human, we don't really need the coccyx or a tailbone. Do humans have tails? No, okay, we don't, but our ancestors may have had that tail and had a purpose for that. Okay, so that's the structure of vestigial structures. And here's just one more example, having muscles in our ears. Okay, do we use those muscles for anything? But unless you're using them for ear wiggling, it doesn't make a difference for survival. Okay, so what are the muscles doing there? Okay, so that's kind of all examples of vestigial structures. Later on this week, you guys are actually going to be doing a different activity with human vestigial structures. So it's a pretty cool activity. You'll kind of look at other body parts or organs or structures in the human, and to talk about what was it there for? Why is it there, and does it serve a purpose? The fourth piece of evidence to support the theory of evolution is embryology. So if you look at the root of that word, embryo, okay, so embryo is like the early stage of, when egg and sperm form to make a zygote. Okay, so early on that zygote forms into an embryo. And then logy is the study of, right? So the study of embryos. So embryologies, or embryos of all vertebrates, are very similar early on in time, in vitro, in the womb, okay, of the mammal or whatever organism it is. Very, very, they look very, very similar earlier on, and then over time they differentiate based on those specific characteristics that that organism possesses. So if you look here, gill slits, tail, notochord, eye, and ear locations, all of those are examples early on that the embryos look very similar. So if you look here at this visual, this is a fish, a reptile, a bird, and a human. So they kind of just like look like foreign little people or structures, but they actually have a lot of common features. Okay, that gill slits, the tail. If you see here, these are the gill slits. Humans, we don't have gills, but we have lungs. Okay, so if you talk about early on in life, we develop out of those gill slips and we eventually get lungs, right? But some of the other, like a fish, they have gills, right? So they're going to keep those gill slits. But early on, it's very hard to decipher the difference between all of those embryos, and that's the purpose. You can see here's a chick embryo and a human embryo. The pharyngeal pouches, the postanal tail. Again, those structures look very similar early on. We know now kind of what they're going to differentiate into, but early on in the stage of life, it's very hard to distinguish. And then the last piece of evidence, so this is the fifth piece of evidence to support the theory of evolution, is biochemical evidence, which is basically just saying the DNA. We have similar DNA sequencing, we have similar DNA codes amongst other organisms that are most like us. Okay, and you're going to again do another activity later on the week dealing with this. So DNA with more similar sequences suggests species are more closely related. Proteins, which are the building blocks of life in all organisms, are composed of the same sets of the 20 amino acids. So amino acids kind of link up together to make a specific protein, and proteins are the building blocks of our life, not just our life, all organisms out there. So if you look here at this little visual, you can see humans and chimpanzees share more than 98% of the identical DNA sequencing. Okay, because if you think back, or you think we're very closely related, we aren't chimpanzees, we're not gorillas, we're not monkeys, right? But if you trace our lineage back far enough, there's probably a common ancestor that we shared more closely than maybe a human and a bird. Okay, but in essence, all the organisms that exist on life shared a common ancestor at one point in time in our world. It's just, is it more recent? And recent is a relative term. It could be, a million years ago versus maybe a billion years ago. And then if you look at this visual, again, you're going to be doing activity later on the week that kind of explores this concept a little bit further. But if you look at the human, okay, so number of amino acids that differ from a human. So obviously they're all the same, right? But if you look at the rhesus monkey, there's only 8 differences. Okay, if you look at the mouse, there's 27 differences. Then a chicken is 45, a frog is 67, and a lamprey is 125, right? So if you're comparing the human with all these other organisms, you would say that the human and the monkey are more closely related. Okay, they more recently share a common ancestor. But if you compare a human and a frog, for example, they're more distantly related. They in the distant past to share a common ancestor, but they still could be related. Okay, and then if you can kind of see this is kind of a similar concept discussing that DNA chain, or the polypeptide chain, or the amino acid chain, or the protein chain. Okay, how many similarities and how many differences exist. Okay, so I just wanted to take a couple minutes right now. Thank you for your attention if you kind of listen the whole way through, to go over the evidence on the theory of evolution. If you have any questions, please feel free to reach out to your teacher. I'm sure we would all love to go over anything that you need clarity on. Thank you. Have a great day.